sorry about the delay that I myself never expected. All right. Okay, thank you for kind introduction. And most of all, I would like to thank you all in this classroom and those attending my presentation on Zoom also. I do my best to, make you happy during my presentation. So I really hope you enjoy my presentation and find my presentation was fruitful at the end of my presentation. All right. Okay, I was introduced already. So the title of my talk today is Researches on ORAN at Hanyang University with emphasis on front halls. Front hall is nothing but a connection between radio unit and distributed unit, which is at the front part of radio access network. All right. Actually, I did this work in my lab with my graduate student at the beginning stage, but most work that I'm presenting today has been done within my company that I myself founded a few years ago within Hanyang University campus. Okay, these are the contents of my talk today, and we'll see what it is as I go ahead. Okay, first chapter, Introduction to ORAN. So we'll see. So first of all, what is radio access network? Most of you must have known this very well. Radio access network is together with core network. Radio access network composes the entire base station system, okay? So as you can see, radio access network, number one, radio access network implements RAT, WCDMA, WebDM, 4G, 5G, that implements RAT, and also it links user equipment to core network. So if you look at this figure, you can see the role of RAN radio access network in more detail. So during uplink, radio access network receives the signal, RAT signal from user equipment and maps the RAT signal into corresponding zeros and ones binary sequence. Then the binary sequence is tossed to core network who routes the binary sequence to the destination. That's what happens during uplink, and during downlink, exactly the same functioning is provided in the opposite direction. So personally, I view radio access network as a mapper, which maps RAT signal into corresponding binary sequence for uplink and maps the binary sequence back to RAT signal during downlink, okay? While core network can be seen as a kind of router. So we have mapper and router as an infrastructure system, all right? So with that, we want to see how that mapper radio access network has evolved. At early stage, we have this structure, which is denoted as distributed radio access network, in which you have antenna and radio unit and base unit at every cell site. So each cell site has antenna, radio unit, baseband unit all together at one place. Okay? So this is what they call DRAN. I think I took this picture from the classroom of Dr. Reed and Dr. Tripathi, and his base station must correspond to DRAN, right? Thank you for this nice picture, Dr. Tripathi. Now, borrowing the state-of-the-art technology from semiconductor industry, we can implement all the baseband signal processing functionalities required on many base station systems at one place, which is denoted as BBU pool, and that is normally installed at separate place, more centralized location, separately from cell site. So in this structure, you have just antenna and RF transceiver at each cell site. All the baseband signal processing part has been moved to more centralized location. That's why people call this centralized RAN. But the BBU pool, which includes all the baseband signal processing functionalities required on many base station systems, BBU pool can be seen as a cloud. So this structure can also be denoted as cloud RAN instead. Also, if you look at the front hall interconnecting number of BBUs at BBU pool and many number of RRUs with each other. So using what? Using virtualized local area network. So this part, front hall, which connects RRU, BBU with each other, this front hall is implemented using virtualized local area network. So this structure sometimes referred to as virtualized RAN. Okay, so the same structure can be referred to in many different ways, but naming is not important at all. What is important is as follows. Each BBU in BBU pool can further be divided into two units, CU, centralized unit, and distributed unit, for providing more flexibilities, okay? So at this stage, network operator guys thought as follows. What if we provide complete transparency on front-haul interface protocol, middle interface protocol, and backhaul interface protocol, like this. If we open the interface protocol of front-haul, interface protocol of mid-haul, interface protocol of backhaul, then completely open to the third party. Then each unit, RU, DU, CU, can be provided by all different companies. Okay? As long as your RU completely satisfies all the requirements of the associated protocol, then RU, you can provide RU independently from DU provider. Similarly, front-haul interface protocol, middle interface protocol is completely open. The DU can be provided by one vendor, which can be different from CU provider and RU provider. So that's what Open RAN is about. When you say Open RAN, what you are opening is not the unit itself. What you are opening is interface protocol between neighboring units, okay? All right. But ideally, theoretically, if you open, as I said, all the interface protocol of front haul, middle, and interface protocol for backhaul, then of course, RU, CU, DU can be provided by all different companies independently. But practical situation is unfortunately, well, I don't know whether it's unfortunate, fortunate. The reality is DU and CU is provided mostly in one body by one of these five big guys, Huawei, Ericsson, Nokia, Samsung, and NEC. If you want me to include just one more than Fujitsu. So at most, one of these six big guys is implementing DU and CU, mostly, in most cases, as one body. Okay? You don't see what interface protocol was employed for mid-haul, right? So it really does not make any real, it's not really meaningful in practice to open the middle interface protocol and backhaul interface protocol. But look at the front haul. If you open front haul interface, then RU, which is most front part of radio access network, can be provided by many small companies. Even an individual person like you, like me, can be a radio unit provider, right? So that's why we want to focus on front haul today. Okay. So what is Open RAN? The key thing is we want to allow baseband unit and radio unit to be supplied by all different guys. Okay, that is the key thing when you see the term Open RAN. Okay. So this is my radio access network. Up until 4.5 generation mobile communication system, you have two units composing radio access network. One is remote radio head, remote radio unit, whatever you might call it, RRU or RRH, and BBU. Okay. Now for 5G, BBU has further been divided into CU and DU. So now in 5G radio access network, you have three units composing radio access network. One is central unit, distributed unit, bus, and radio unit. So now we are ready to summarize what ORAN is. What is ORAN? ORAN is nothing but a disaggregated radio access network. Disaggregated into 3 units, CU, DU, and RU. And you are opening interface protocol between every neighboring unit so that each unit can be provided by all different guys. Okay? That is the key point of Open RAN. Now the question is, okay, you said up until 4.5G mobile communication system, we have used eCPRI as a protocol for front haul. Can you use the same protocol, eCPRI, for 5G? Well, unfortunately, the answer is no, because of many issues in eCPRI. Okay? Among those many issues, we have 2 major issues existing in eCPRI. Number one, eCPRI is circuit switching based protocol. It's not efficient enough. It's not flexible enough to be used for 5G radio access network. Number two, eCPRI is, as the name implies, CP, common public radio interface. It's supposed to be common public, but it's not common public at all. Because eCPRI includes many vendor specifics, many vendor dependent, things is included in eCPRI. So we want to get rid of these 2 problems and make a new interface protocol for front haul for 5G radio access network system. So with those 2 problems existing in eCPRI, in their mind, these 4 big guys gathered together, Huawei, Ericsson, Nokia, and NEC. Okay, now you guys make a new interface protocol for connecting node 1 and node 2. Node 1 is denoted as REC, which is written down there, and node 2 is RE. So we want to make a very generic protocol for connecting node 1, REC, and node 2, RE. All right? How? So the answer is eCPRI. All right? Now, we want to make protocol in that way. You have U-plane data transmission. You have control plane. You have management plane. You have synchronization plane. And I want to define protocol for U-plane data transmission, protocol for C-plane data transmission, and therefore M-plane data transmission, S-plane data transmission, all independently, so that each protocol can evolve independently, giving us a lot more, really a lot of flexibilities. Okay, what is that? What is user plane messages? What we want to transmit between ORU, ODU, and ORU, from ODU to ORU for downlink, from ORU to ODU for uplink. What we want to transmit is complex valued OFDM sample, right? So real part and imaginary part of that OFDM sample is to be transmitted between ODU and ORU as user plane data. So when you say, so just I component and Q component of that OFDM sample itself is a user plane message. Okay? What is then C plane message? C plane message. In order for this U plane message to be transmitted successfully without any error, you want to transmit subcarrier information and subcarrier index and symbol index before you send S plane message. Before you send that complex valued OFDM sample, you want to specify, oh, this sample, which you will soon receive, corresponds to this subcarrier index and this symbol index. That's what you are sending as C-plane message. Okay? Now, is that enough? No. In order for 2 nodes to communicate with each other successfully, each one must know his counterpart very well. So how many antennas are there in radio unit? What about the carrier information at each antenna? What about the timing information at each antenna? Exactly which moment, when each antenna must shoot the signal, downlink signal, and at which time the uplink signal is expected to come at each antenna. All these antenna-related parameters and packet-related parameters, how many bits are going to use for specifying I component and Q component? And these kind of packet-related parameters and antenna-related parameters, they are M-plane messages. So at the beginning, ODU sent a bunch of parameters to ORU. Hey, you set up your state with these parameters. Then ORU sent me back his acknowledgement. I'm sorry, I have just two antennas. His state is sent back to ODU as a response. So we use M-plane messages for communicating, this kind of information. So M-plane is, M-plane message is parameter values. And of course, S-plane, synchronization plane message is responsible for synchronizing all the units, control unit, central units, distributed units, and radio units, okay? So now we have understood what U-plane message, C-plane message, M-plane message, and S-plane message is, okay? Now, so with that, I want to show you what eCPRI protocol is at the next page. But before we go to the next page, let me show you the eCPRI packet. Here, I have eCPRI packet with 4 bytes as its header. Look at the second byte. We have eCPRI message type. With 8 bits, I can define 256 different message types. Okay? See, eCPRI has developed by these 4 big vendors as very generic protocol. So eCPRI takes care of every different kinds, 256 different kinds. But when you use eCPRI protocol to ORAN application, you use just 2 cases, just 2 message types. Number 1, when these guys are eCPRI message type, that bit is all 0. That's type 0. Then you have IQ data as a payload. Where's my cursor? You see, I could have the mouse. But anyway, all right, that's okay. So when eCPRI message type, can you see my finger? Goes on the Zoom. All right. Message type is all 0, then you have IQ data as your payload. That means when they are all 0, you have U-plane data. When they are 2, 0, 0, 0, 0, 0, 0, 1, 0, then you have real-time control data, which means you have C-plane data here. That's it. You don't use any other combination. So when you apply eCPRI protocol to ORAN application, you use very small portion of eCPRI, which was made as a very generic, but so we are going to restrict ourselves in those 2 cases because this is ORAN presentation. We are not interested in any other application, right? So let me give you then how the C-plane data and U-plane data is transmitted between ODU and ORU using eCPRI protocol. All right? We use this 3-layered protocol stack for the transmission of U-plane data and C-plane data. Okay? You have ODU, ORU. You have front haul has been implemented with virtualized local area network, with Ethernet, okay? Ethernet. So physical layer is Ethernet. And transport layer is eCPRI, which I just explained in the previous page. And application layer is ORAN. What does that mean? That means this. We want to transmit for the first symbol period, we want to transmit yellow, violet, green resource blocks. But in ORAN, we never use the terminology resource block. Instead, we use sections. We want to transmit yellow section, violet section, and green section using this packet. So first transmitter, suppose is downlink. Then transmitter is ODU. ODU will map this thing into the packet, ORAN payload. And the transmitter will put ORAN header specifying the section type. Well, ORAN header has 8 bits reserved for specifying section type. Once again, with that 8 bit, you can define 256 section type, but we have only section type 0, section type 1, 3, 5, and 6. We are using just 5 different section types. Section type 0 is used when you deal with these non-specified sections, okay? So you transmit all zeros with section type 0. Section type 1 is ordinary downlink and uplink. The value, the complex ATM symbol will be mapped as it is as ORAN payload, okay? And section type 3 is reserved for you to deal with PRAT channel data or the case of mixed numerologies. It's a little complicated, but if I have chance, then I'll talk about that later. Anyway, you specify section type at ORAN header. So these guys is packed up as ORAN packet. Then you append eCPRI header at the beginning part, specifying whether that is S-plane data or user plane data or control plane data. Then finally, you append physical layer Ethernet header to specify the address used in virtualized local area network. Okay? Then this physical layer packet is transmitted from ODU to ORU for downlink, from ORU to ODU for uplink. Then receiver will receive oh, I got the cursor, receive this physical layer packet at the beginning, and he decodes first. Receiver must decode Ethernet header, and he knows, oh, this has been addressed to me. Then he decodes eCPRI header, then he knows whether he has received user plane data or G plane data. Then he decodes ORAN header, then he knows how to map the ORAN payload back to original OFDM sample values. Okay? So this is how C plane and user plane data are transmitted between ODU and ORU. Similarly, based on, using eCPRI protocol. Similarly, S-plane data and M-plane data is transmitted between ODU and ORU using, multi-layer protocol. All right. Once you have understood up to here, we have understood more than 75% of ORAN already. Okay. So we want to know how the S-plane, U-plane, C-plane, M-plane, and S-plane data is transmitted between ODU and ORU. Now we are ready to see how I implemented the radio unit, actually hardware implementation. All right. First, we developed proof of concept system in year 2020. Then it's an emulator of ODU, emulator of ORU, and emulator of user equipment. Okay. Then, from that experience, we developed a commercially applicable radio unit for our customer, Japanese network operator, the largest Japanese network operator in Japan. with these key features. I will talk about the features later. Then we modified this radio unit such that my radio unit can be connected with another distributed unit developed by another vendor, Nokia, within the network of Korean network operator LGU+. Then finally, I am now expanding my radio unit such that a single radio unit can control number of daughter radio units. Okay? I don't know why people use daughter in this case, not son, because if your name is son radio unit, then he's not obedient enough. So to make it obedient, you call it daughter radio unit. My daughter was very obedient because, okay. Now, let me show you how I implemented proof of concept system. All right, we did that in the year 2020. So actually what we did was we implemented audio emulator using Texas Instruments DSP, ORU emulator with USRP, and EU, user equipment emulator using another DSP, okay? And this is about the functional split. So I'm going to skip this because you must have known this pretty well. Anyway, the key point is that we are considering functional split 7.2. That means low-fi as well as RF transceiver functionalities will be put on my radio unit, and all the other Phi signal processing part, which is denoted as hi-fi, is put on DU, okay? Actually, we are not very interested in this RRC and PDCP, RLC and MAC, okay? Because ORU does not have to worry about RRC and these kind of things, because all the parameters obtained by RRC, PDCP, and these things is coming to radio unit as end-frame messages. So I don't have to think, well, what is the origin of this parameter? Who made this parameter? I don't have to worry about that. I just use the parameters and use that when my radio unit is set up, okay? So those are parameter values just to be used for setting up the radio unit, okay? Don't need to try to trace who made these parameter values, okay? Now, so my ODU emulator here, my ORU emulator here for downlink and uplink. Now, for downlink, my ODU works as a framer. When I say framer, means OFDM sample values is mapped into corresponding packet. That procedure is denoted as a framing. So transmitter performs framing procedure and receiver receives the packet, then he has to remap this packet value back to original OFDM sample positions. Okay? So framing, deframing is performed at transmitter and receiver respectively. Okay? Transmitter is ODU and receiver is ORU for downlink and the other way around for uplink. Okay? So, and this figure includes movie files. I hope you can enjoy. I have made kind of demonstration environment using two FPGA boards. One FPGA board is transmitter, and the other FPGA board is receiver. Transmitter will be ODU, receiver will be ORU for downlink, and the other way around for uplink. Okay? So transmitter, I perform framing procedure. So OFDM sample values is mapped into ORAN packet first, appending eCPRI header, it becomes eCPRI packet, then appending physical layer Ethernet header, it becomes physical layer packet, then transmitted via 10 gig Ethernet port. Each 10 gig carries 4 independent data streams to support 44 MIMO. Since I have 4 10 gig in parallel, I can handle 16T, 16R MIMO system. Okay? Checking out our capability of dealing with 40 gig bps data rate, okay, we are now ready to make, I will skip this one. So this is all related with that movie file. Now we are ready to make real emulator. So these are the functional blocks. These are the functional blocks to be covered by ODU emulator, and these are the functional blocks to be covered by ORU emulator for category A. And these are those for category B. The only difference between category A and B is ORU takes care of pre-coding as well as FFT processing. Whereas that pre-coding obligation falls on ODU in category A, okay? We have implemented emulator of ORU for category A and category B, okay? Now, this is the photograph of USRP, which implemented ORU emulator, okay, which employs 2 daughter board, once again daughter, 2 daughter board to support 2 antenna array system to provide a nice shaped beam pattern to the direction of user equipment, okay? We'll see that later. This is the principle of beamforming. Now we are ready to make ODU emulator, which takes care of all these functionalities, okay? With Texas Instruments board, I implemented that. And these are the functional blocks implemented on Texas Instruments DSP. As you see, I'm not considering MAC and RLC, okay? I'm just generating 5G or 4G compressed valued data samples, okay, for each single period. Then that is what ODU emulator is doing. So generating the data, and that data is sent as a downlink packet to ORU emulator, which performs inverse Fourier transform, and beamforming parameters are multiplied for these 2 antennas to provide a nicely shaped beam pattern to the direction of user equipment. Okay, these are the experimental environment here. Okay, here I have ODU emulator, ORU emulator, which employs 2 antennas, which provides nicely shaped beam pattern to the direction of user equipment antenna. And also I have another antenna to check the receiving power. Okay, this is what I have received at user equipment emulator before channel compensation, after channel compensation, and these are the channel compensation value itself as a function of time and frequency. Okay, this is constellation received at user equipment when the beam is correctly pointing the user equipment. This is when I have dispointing error by 30 degrees. I have just 2 antenna elements, so it does not give me very high angular resolution. So even with 30-degree mispointing error, I can see acceptable constellation, but just a little bad error vector magnitude, EVM, okay? This is when you have correct beam pattern, your receiving power is about 10 dB higher than when you have angular error. Now, okay, I'm sorry to be too much badly hurried. So, all right. Now we are ready to see how I implemented the commercially applicable radio unit. that was provided to my Japanese customer. Okay, now we are ready to talk about this part. Okay, and the name of that company is blocked because I have not received the approval from my customer. But actually, I have not made the contract directly with this Japanese network operator. I made a contract with Korean small company, Korean vendor, Samji, and Samji made, this Korean vendor company made another contract with the Japanese vendor, who made final contract with the Japanese network operator. This kind of hierarchical contract is not surprising at all in the base station market. Everybody does this. And even my customer knows this hierarchical contract system. But only the final contractor, Japanese vendor, is seen to the Japanese network operator. All the other guys, including myself, is not seen to them. Okay? All right. So the front haul has been implemented using 25 gig Ethernet. It's a lot higher than 10 gig Ethernet, which we used to use previously. So it's a lot higher, 25 gig. So you need to employ for the correction. So employed with Solomon code, and it worked very well. And once again, front haul is virtualized local area network, and we employed PTP, very well known synchronization protocol as S-plane application protocol. Okay, this PTP was released by IEEE many years ago, and this is important. Okay, this site has provided very nice experimental equipment. It works as a ODU emulator. So this experimental kit provided by T-Site is named ORS, ORAN Studio. This ORAN Studio generates downlink packet. And we receive downlink packet over the virtualized local area network. So once your radio unit can handle this downlink packet successfully, then you are completely proved as a developer of successfully working radio unit, as far as you are concerned with downlink. Okay? And after that conformance test with T-Site ORAN Studio, I provide my system to my customer. Then my customer, Japanese network operator, performed input-output test with Samsung's audio. Then he did that with Fujitsu's audio, and he did that also with NEC's audio. So my radio unit has been proven working okay with 3 different audios provided by 3 different vendors. And they did perform the field test also, okay, here. And all these key features will be discussed later. Now, when you make a contract with network operator, they will give you this requirement. This is just part of requirements, okay? So FC means full consideration, NC is no consideration, and PC partially consideration. Is, I don't know whether it's correct English. It's Japanese English. So FC, you have to fully consider NC and PC. Anyway, UDP/IP is excluded. That means, how can I go back? All right. So I told you for S-plane message and C-plane message transmission, we employ 3-layered protocol stack. At the physical layer, we have Ethernet. At the transport layer, we have eCPRI. At the application layer, we have ORAN. Okay. And UDP/IP is optional, is excluded by the request of my customer. Okay. So you are given all these requirements from your customer with FC, NC, PC specified. Then this part is what you are answering to this requirement. Okay. Okay, now we want to see a little more detail about M-plane message. I said, what is an M-plane message? M-plane message is a number of parameter values, okay, with which your ORU, radio unit, is to be set up, okay? At the beginning, before the communication starts, ODU sends you a bunch of parameters. Hey, you set up your mode with these parameter values, okay? How many antenna and carrier frequency specification and timing information you have to send the downlink signal at this timing, and you are expected to receive uplink signal at this timing. All these antenna-related parameters and packet-related parameters also are included in M-plane message. So M-plane message is a list of parameters, bunch of parameters that ORAN, ORU, radio unit, is to be set up with, okay? So, and that parameter values is explicitly described using Yang. Yang, in this case, is not a Chinese family name. Yang is a computer language developed for data modeling, okay? So we use Yang to describe all these parameter values to be used as my M-plane message, okay? So we have antenna-related parameters and packet-related parameters. You can take a look at each item later. Now, this is a part of M-plane message, which is about latency requirement, okay? Why do you have this thing at the top which blocks? Anyway, okay. Now, we are talking about communication between ODU and ORU, distributed unit and radio unit, okay? Oh, all right. So now, as radio unit manufacturer, as a radio unit provider, I have to guarantee that my radio unit keeps the latency requirement for the signal to flow from node number 2 and disappeared. From 2 to A. A stands for antenna. So for downlink, the signal must flow 2 to A. For uplink, signal must flow from A to 3. Then I must guarantee that this is my maximum latency, this is my minimum latency for the signal to flow to 2 to A for downlink, from A to 3 for uplink. And, okay, let me finish this slide, okay, very quickly. And all right, this is kind of very interesting. Believe me, interesting. All right. See, the top, we have symbol index, okay? Symbol 0 is the moment that you have to shoot your downlink signal to the user equipment. And symbol period 0 is the moment that you are expected to receive uplink signal from user equipment, okay? That is a reference time. Now, why so strange looking characters? All right, no problem, no problem. Now, this yellow thing, this one, yellow thing, okay. Yeah, can you use the laser? But somehow I do not have that toolbox in my screen. So that is only in your screen. So, oh, sorry. Yeah, I finally, Thank you. This is one of the 1,000 reasons I want to have in my presentation. Oh, please, please. Oh, okay. All right. All right. Now. Oh, yeah. If you are busy, then please feel free to leave anytime. All right. Now, in order for the downlink signal to leave your antenna at this moment, you are expected to receive the corresponding user plane data at earliest at this moment, at latest at this moment. That is what is specified on the top of the table. 134 microseconds is the minimum, and 345 is the maximum. This is the window that you have to open to receive the U-plane data. Okay? So my radio unit received the U-plane data during that time period, at earliest this moment, at latest at this moment. Then what is important is, as soon as you receive the downlink packet, you have to perform this framing procedure, right? You have to map this packet back to original OFDM sample position. Okay? Then you have to perform inverse Fourier transform on that. Then you have to perform D to A conversion and frequency up conversion and shoot the signal as your downlink at that time, 0. So this T of 2A is the time that is given to you to finish all the required functionality. All right? Before you receive this user plane data, actually you will receive control plane data 125 microseconds before you receive user plane data. You receive control plane data, which tells you the carrier index and symbol index of the user plane data that will soon arrive at your end. Okay? And for uplink, this is the moment you are expected to receive the uplink signal from the user equipment. And that information is given from upper layer as whole strange characters. Somehow I lost. Okay, from this time and this time, your upper layer tells you you are expected to receive uplink data, uplink signal at this timing. That message is coming on C plane. That information will arrive at radio unit at earliest this moment, at latest at this moment. Okay? Indeed, you will receive uplink signal during that time period. Then, as soon as you receive uplink signal, you have to perform frequency down conversion, A to D conversion, and forward Fourier transform and framing procedure. You have to map these complex values, which is the result of forward Fourier transform, into packet. You have to change these OFDM sample values into corresponding packet. Okay? So you have to pack up all the OFDM sample values to be loaded on packet, and you are complete making physical layer packet by this moment. 171 microseconds after you receive the uplink data, you have to finish all the deframing all the framing procedure, right? What if we do not keep this requirement? What will happen? Then you will break the timing. I don't know. I really don't know what's going to happen if you cannot keep that timing requirement. It will depend how much margin your customer is reserving, okay, preserving. But if they do not have enough margin, then they will destroy all the procedures. But one thing clear is if you do not keep this requirement, they will not pay you. That's one thing clear. That's actually what happened to us. So, okay. This is how I made the ORAN difframers. Okay, when packet is coming from ODU to ORU for downlink, ODU is sending you packet. When you receive the packet from ODU, this is a physical layer packet, meaning that this is Ethernet packet. Then you decode the header, then you find, oh, this has been addressed to me, okay. Then you are left with eCPRI packet, then you decode eCPRI header to find whether you have received uPlane message or cPlane message. Okay, oh, this is cPlane or uPlane message, okay, fine. Then you finally decode ORAN header, then you know how to map this payload back to original OFDM sample position. And this is how to decode the ORAN header. ORAN parser is decoding ORAN header, okay? Before this IP, you have eCPRI deframer, and before that, you have Ethernet deframer. You receive the packet from ODU, then first you decode physical layer header, then you decode eCPRI header, then you decode ORAN header, okay? Because we are using 3-layered protocol stack. This is how I implemented uplink framer, ORAN framer. When radio unit receives uplink signal from user equipment, after frequency down conversion and A to D conversion, it performs fold Fourier transform. I'm supporting 44 MIMO, so that's why I have 4 parallel processes, right? So each processor takes care of corresponding antenna signal. So you take fold Fourier transform, then after you take fold Fourier transform, you have to map this complex valued OFDM sample into packet. So first, that maps to ORAN packet with ORAN header specifying the section type. Then you append eCPRI header. It becomes eCPRI header, eCPRI packet. Then you finally append physical layer Ethernet header to specify the address of this virtualized local area network. Then you cast this physical layer packet to the receiver. In case of downlink, receiver will be ORU. In case, well, here we are talking about ORU, so ORU is sending, we are talking about uplink, so ORU will send the packet to the ODU. Then, similarly, when ODU receives this packet, he will perform deframing procedure, mapping the packet value back to original OFDM sample positions, and ODU will perform high-fi procedures, okay? Oh, this will be the last page that I'm going to cover today. So be patient just for last 2 minutes, 3 minutes, okay? Okay. We have invested a lot to buy this equipment from Keysight. Very expensive. This Keysight instrument works as a ODU emulator. And it provides downlink packet with every requirement of your customer being reflected. So your customer, I just show you the requirement of my customer, and all those requirements should be reflected when the downlink packet is generated. Okay, so my ORAN studio provided by Keysight company. This ORAN studio provides me downlink packet over the virtualized local area network. Then this is how my final product look like. My radio unit that I provided to Japanese network operator. Okay, I am radio unit. I received the downlink packet generated from audio emulator. Then I perform deframing procedure and inverse Fourier transform and D2A conversion and frequency up conversion and shoot it to the user equipment as a downlink signal. Okay. Now, if this procedure can be successfully done, then you are proved okay with downlink signal, because what you have processed with is the downlink package which includes all the requirements of your customers. If anything goes wrong, even if there's no problem with that procedure, then the reason is one of these two. Your radio unit has problem with uplink signal, or your ODU is wrong. So if your radio unit is okay with that simulation, if your radio unit is okay, working okay with Keysight downlink packet, then you are okay with downlink. Proved. Okay? So this equipment works in two modes: signal generator and vector analyzer. Okay? So after you process the downlink packet successfully, you send it to this analyzer, then check the performance. Okay, if downlink processing is okay. Then for uplink, this equipment provides uplink signal to my radio unit. Then radio unit performs framing procedure. It receives uplink signal that has to be mapped into packet. Then uplink packet is sent to this ORAN studio. Then it's analyzed. Okay. All right. So this is my final product, radio unit, delivered to Japanese network operator. These are the explanation about each equipment. These are the things that you can check as M-frame messages. Your ORU periodically send its state to ODU. Hey, I am dead. Well, I'm alive. This kind of things, okay? But temperature, even temperature and everything is reported to ODU periodically using PTP/IP protocol. Really, I promise you, this is gonna be really the last page. See, now suppose your radio unit works okay with downlink packet provided from Keysight ORAN Studio. Okay, now you have proven okay as far as you are concerned with downlink processing. So you provide your radio unit to your customer Your customer say, oh, it does not work. Then you have two possibilities. Number one, his DU is wrong. But normally that does not take place. Number two, reason number two, you are wrong with uplink processing, which happened to me, unfortunately. Now, I had a problem with uplink signal processing. I know when the signal arrives at my antenna because I'm given that timing information from M-plane messages. Okay? So I observe the error vector magnitude. This is the moment, the pink is the moment I was given as a M-plane message from upper layer, from audio, okay, as an M-plane message. So I checked, I performed FFT. So when you receive the signal, uplink is you are receiving the signal from user equipment. You receive the uplink signal, then you have to perform forward Fourier transform. When you perform forward Fourier transform, you make it sure that the starting point is correctly set up. Starting point is somewhere in between CP. It should be long enough, which is longer than channel dispersion, which should not be too much longer than CP period. But, so you are given that timing information from uplink. So I just trusted it. So I do it with that information. But I soon find that I made a mistake by myself. Of course, nobody makes mistakes but you, right? So because of processing delay, this is the moment I received the Pirachi signal. This is the Pirachi signal. By the way, Pirachi signal, physical layer, physical random access channel, right? With that channel information, your upper layer identifies the user equipment. Anyway, we have some channel named Pirachi, okay? Which is a little more headache than normal signal, okay? Now, because of its longer duration.
For Q&A for people to ask questions. So don't know if we have much. Is it class
Okay. We'll be finished within at most 1.5 minutes. Okay. So I was thinking that I will have uplink signal processing delay by this much. But what really happened was, this headache caused me to have a little longer delay because Pirachi is a lot longer than normal symbol period. This was Pirachi format 0, the 4G Pirachi, which is stupidly long. So Pirachi starts from here where normal uplink signal PU, SCH, PU, CCH starts from here because of the delay difference. So you start your FFT function with some extra delay on Pirachi signal. Right? So you start with FFT from here for non-Pirachi, but don't use the same value for Pirachi. You have some additional delay for Pirachi because you have appended some additional delay on Pirachi sender. So that by the amount of that additional delay that you yourself appended on Pirachi, you have to have a little extra delay. So with additional delay on Pirachi, see, everything was cleared up. So this is the end of my talk today. So I'm sorry to be too much bad hurry. Sorry. Thank you.
Thank you very much. There might be some questions. So.
Oh, yeah. Okay, sorry. Because I was in too much hurry, so if you have any question later, then I'll be happy to, reply your question or comment. Please send your question or comment to my email account anytime. Then I'll be happy to send you my reply. And once again, thank you very much for coming to this presentation. And those on Zoom, I really appreciate your extremely precious time.
So thank you, Professor Choi, for the presentation. And since no one asked, let me ask a general